Quick question before we start. Has anyone tried posting a discussion on the forum? Is it actually working? Reminds me I have to bring up chat. Give me a sec. Yeah, because I posted that one, and I'm not sure it's I'm not sure it's correct. I was told that Brightspace is preferred over Piazza for doing class discussions. I pulled Reddit to find this out, and and oh, it's so bad, and their mobile app is completely like awful. Oh, that's cool. We have a question in the chat. Let me see. Can I debug this for you? Oh, okay. Yep. Yeah, so office hours will be on Zoom. They won't be live streamed. And it's 8:30 to 9:30 p.m. on Thursday. Nope, nope, just join the so for the normally scheduled office hours, just join the Zoom call and we'll just be hanging out, and you're welcome to like call in and work on the lab during the call if you like. And okay, let's give stragglers another minute to get started to join us. Looks like the Twitch stream is up. This time I will actually remember to record. I'm helping someone debug their Haskell setup. Let me check something real quick. All right, it is 4:56, so let's go ahead and start going. I see there's some requests for help for installing Haskell. We'll get to that very shortly, but if you haven't been able to install it locally, remember that there is also a instance of Haskell on the CIMS server, which I'm going to post to the Zoom chat. Let me get and everyone in the class should have access to it. And you can use that to get a quick and easy copy of Haskell. If you can't access that either, I believe you can also use Replit to get a Haskell file and session going. Although I haven't tested it before this class, but you might also give that a try. Okay, let me just welcome everyone. Hi, everyone. I'm hoping that the Twitch stream is working. There's no one here, but at least the Zoom stream is working, so that's the important part. Welcome. We'll be talking about Haskell today. And basically my goal for today's lecture is to teach you enough Haskell so that you can do the first homework, which, by the way, is due on Monday. And if folks are like, oh my God, you know, this is too little time, I'll consider giving a blanket extension to Tuesday. By the way, on the Monday lecture, what I plan to do is I plan to go over the lab. So to get the most out of it, like, I encourage you to try the lab on your own, and then on Monday at class, we will actually like step through it and see what's going on. But first, I want to tell you a little bit about Haskell. Looks like the Twitch stream is working, so that's great to see. All right, so what's going on with Haskell? So why are we teaching Haskell in this class? Well, in last time's lecture, I talked about a bunch of things that we wanted to discuss in this class, and Haskell is very heavy in the say more with less category. So we're going to talk about first class functions, we're going to talk about pattern matching, type inference, type classes, monads. These are all the features that feature very heavily in Haskell, and so it's like, Haskell has been pretty successful in the sense that many of the features that were pioneered in Haskell are now available in many other languages. For example, a recent one is type classes from Haskell have made their way into Rust as traits. So if you know how Haskell type classes work, you also know how Rust traits work. And that's pretty cool, you know, seeing things spread out in that way. And so because Haskell is like really built around these features, you really can get a nice understanding of them. It's very nice to work with functional programming and all of these things in Haskell. And so hopefully you'll get some sense of that while we're doing it in the class. And concurrency is sprinkled in near the end because Haskell, because it's what we call a pure language, and I'll tell you what that means in a moment, means that it has a very interesting approach for doing concurrency. And that makes it a really good study case for how to do concurrency in perhaps a way that wouldn't be that feasible in other languages. So what is Haskell? So I'm going to give you 4 adjectives, and I want to explain what each of these adjectives are. So Haskell is a typed, lazy, pure, functional programming language. So let's just go through each of these one by one. So 1, Haskell is a functional programming language. So what do I mean by functional? No, I don't mean that like it actually works compared to dysfunctional languages that don't work, although haha, that's a funny joke. What I mean by functional is that it's all about functions. So so there's 2 ways we can think about this. So one is that functions are first class. Remember when I talked about JavaScript, right? JavaScript said, hey, functions are values, you can pass them around, you know, that's pretty cool. But there's a second thing that is really big about, really like changes the way you think about writing programs when you write Haskell, which is that we don't write sequences of instructions. So typically, and you know, we often say, what is a not functional language? It's an imperative language. Why do we say it's imperative? It's because what you do is you say, hey computer, first I want you to do X, then I want you to do Y, then I want you to do Z. So you say, okay, step 1, step 2, step 3. In Haskell, you don't do that. In fact, there's no way to like write semicolons until we learn about what monads are, and then we actually like have so-called do notation, which lets us sequence operations. But in classic Haskell, and the Haskell we'll be looking at in class today, there's just expressions. You can only like ever write, you know, hey, I want to write some code, and it expresses some value, and then this value can be used somewhere else. And you're entirely using, you know, functions to put together your programs and do things. And you might be like, wow, Edward, can I actually even write any programs using only functions? And the answer is yes, and you can write a lot of programs. And so, for example, in the lab, you're going to write a UPC code verifier, and you're going to write a nonogram solver. And both of these, we're going to do it entirely with just expressions, and it will be nice and, you know, hopefully enjoyable to do. So that's what we mean by functional programming. In lots of other languages, you can do functional programming. It is a mode of operation that is available to you, and it's really useful when it applies to your problem space. In Haskell, we flip it around. Everything is functional by default, and you have to like explicitly use some extra stuff to get into the imperative mode of thinking. The second adjective is pure. What do I mean by pure? Well, what I mean by pure is that in Haskell, by default, there is no mutation or side effects. So let's just think about a very standard thing you might do in a Hello World program, which is you would say, write a for loop. And how would you set up this for loop? Well, you'd set some variable I to 0, and then you'd say, okay, well, every time I go around the loop, I want to increment this variable. That's a mutation. You're changing the value of the variable, and I'm going to increment it until it gets to some value. And in Haskell, we say, no, that's not something you're allowed to do. You're not allowed to mutate variables. Everything you define has to be exactly the way it is forever. You might ask, well, then how do I do loops? And the answer is we'll use recursion instead to do this, and we'll see examples of this in the live coding segment of this lecture. So there's no mutation, there's no side effects. So when you write Haskell code, once again, by default, you're not allowed to, fire nuclear missiles, or, check what the current date is, or, read in some input from the console. And the net effect of this is that Haskell functions, pure Haskell functions, always do the same thing no matter what you do. There's a question in the chat which is, aren't all functional languages pure? And the answer is no, not necessarily. In fact, Haskell is actually very unique. It is still one of the very few languages that is pure by default. So another language that you may be familiar with is OCaml. OCaml is a very popular language for functional programming. It's used by Jane Street to great effect. And OCaml is not pure by default. So you can, assign references and mutate them, and that's sort of just how things are in OCaml. And so no, you don't have to be pure if you're functional. So getting back to what I was saying, so Haskell being pure means functions always do the same thing whenever you call them, and that actually is a really useful property because it means, for example, that we can reason about Haskell programs more easily because we don't have to worry about when I call this function here, it's going to return a 3, but when I call it there, it's going to return a 5. It's a lot more like writing math. And, a lot of people who write Haskell for the first time is like, wow, it's really like, doing my math class because I'm just defining equations. I'm not mutating variables. I'm just defining equations until I get there. And there's something to it. Like there's a lot of ties to mathematical thinking in Haskell. And it also means that I mentioned that Haskell is good at concurrency, and Haskell's purity is a big reason why this is the case, because when you don't mutate things, you can't have data races. What's a data race? Well, you'll have to wait until we talk about it later. And finally, being a pure language means Haskell code is often a lot more maintainable than normal code bases, because if you see a function and it's pure, oh, this function is only doing some computation. It's not doing any interactions with the rest of the system. So it's very easy to tell, if there's going to be spooky action at a distance or not. And that's pretty powerful. Adjective 3 is lazy. So what does it mean that Haskell's lazy? Well, normally, when you write an imperative program, you say do X, do Y, and then do Z. And when you run the program, it does X, it does Y, and then does Z. But what if X is computing some really expensive value, and you want to wait until later to use it, or maybe you won't use it at all? Well, if you don't use it at all, then you wasted all the time computing the value, and that is slowing down your program. And so Haskell is actually what we call lazy. So whenever you write expressions in Haskell, they don't get immediately evaluated. Instead, you wait until they're actually needed, and that's when things get actually executed. Lazy evaluation is a bit hard to understand, and it's one of the reasons why Haskell gets a rap for being a difficult to work with language. By the way, OCaml, the language we mentioned earlier, it's not lazy. It's a strict functional language. So things execute when you ask them to. But there's some really powerful things you can do with laziness in Haskell. It means Haskell programs are more compositional because Haskell actually doesn't really need any control flow structures, because the fact that things are lazy mean that you can like write a function that takes in a bunch of arguments, and you can rest assured that those arguments won't actually get called until you actually say you need it. So if you're writing if then else, normally that couldn't be a function, or if it was a function, you would have to pass in little lambdas, little thunks that delay the execution of things. But in Haskell, that's not necessary, and it's really useful when you're writing DSLs. So there's a question in chat, which is, are we talking immediately and later until needed within compile time? So laziness here is a runtime concept. So we'll compile everything, and then at runtime, we won't actually calculate values. We won't actually run your program until it is needed. There's another question, which is, does that mean we won't really be able to tell when a function might be executed in Haskell? And the answer is yes, unfortunately. So it can be quite difficult sometimes to understand exactly what is being executed when you're debugging Haskell code. And we'll also look, I need to make sure I have enough time for the live coding, but I definitely, it's on the list, is explaining how to like look into when things are getting executed, because when you're debugging, you're like, oh, I want to know what this is. What I will say is that in Haskell, we often don't need to debug as much because we're forced to write programs that like sort of are easy to understand, and you might see what I mean by that when we work on the homework. By the way, lazy evaluation is sort of one of the reasons Haskell came into existence. So when Haskell was originally being designed, there was basically a bunch of research going on in the programming languages community about how to do lazy functional languages. And Haskell was a committee designed language to basically pull together a bunch of the projects that were in effort to create this vehicle for doing research on lazy evaluation. These days, if you ask people, lazy evaluation, that's kind of weird, like, it kind of is not so great. Would have been better if Haskell was strict. But the purity aspect of Haskell, that is to say expressions aren't allowed to have side effects, came directly out of being lazy. Because, well, if you can't tell when things are going to run, then you'd better not like be doing visible side effects based on what order things run. So Simon Peyton-Jones likes to say, laziness is the hair shirt that keeps us honest when we are being pure. And finally, Haskell is a typed programming language, so hopefully this is familiar. As opposed to dynamic programming languages which don't have types. So Haskell has a type checker. If you try to add an integer with a string, Haskell will complain at you. Unlike other type systems and other programming languages that you may have worked with, Haskell's type system is very strong. Like, you can do a lot of things with it. So you might be used to like being like, yeah, static languages are cool, but I like dynamic languages because I can write the programs that I want to write without having to like go through lots of contortions to make things work out the way I want them to. And what we'll find is that in Haskell, oftentimes the types sort of like, Haskell gives you enough rope to like write the programs you want to write and actually still have types for them in those situations. So just to wrap up, why am I teaching Haskell in the first part of this class? Well, one is I'm a huge Haskell fan, so I teach what I like. But there's some other reasons. So one is that Haskell's types, I think, will change the way you think about how you write programs. Types are, oftentimes people are like, oh, we should use statically typed programming languages because they help prevent errors, like if you pass a string into a function that requests an int. But there's much more to types than that. Types are about like organizing your program. They're like basically about saying, what a function is trying to do, right? Like if you think about in a dynamic language, what's the first thing you write in the doc block? You say what the types of the parameters are going to be and what type of thing you're going to get out in the end. And so when you have fancy types like in Haskell, you can really express a lot about what your functions want to do. In fact, in some situations, a type signature is enough to automatically tell you how a function should be implemented. Like you don't have to do anything else. The type fully specifies the implementation of the function. That's pretty cool. So once you start thinking in types, you won't go back. You'll write all your programs thinking, what is the type signature of this thing in the back of your head? Second, and from the overview of the course, you should have guessed by now, in Haskell, it's a very high level language. We don't tell our computer exactly what to do step by step by step. We instead express at a very high level what we want, and the compiler figures out how to get us there. So it raises the level of abstraction. We can write code that otherwise would be very laborious to do in a much easier way in this setting. And finally, purity is a really useful concept, and it's really important when we're thinking about how to do multi-core programming. Do we have any questions so far about this? This is very high level, so I'm not expecting too many questions, but I do want this to be interactive. So just to finish off these sets of slides with, sort of a little bit about like Haskell's popularity. Most programming languages, and there are many, many programming languages, right? There has never been a better time to write a new programming language. There are so many tools, so many resources. It's great. But most programming languages, will have one user, their creator, and they'll die in short order. And when you're in academia and you're designing a research language, the sort of goal is to have a language that sort of can be used for a few years. You have a few PhD students, you write a bunch of papers about it, and then eventually, you're done, you're going to make some new language, and that's cool. And, contrast that with all of the like really popular languages that we'll be studying later in this course, where they've, gotten so many users that they have passed the so-called threshold of immortality. We cannot kill these languages even if we wanted to. There's too much code, too many programmers using it to actually get rid of it. And, there's also a joke that, languages that are designed by committee just never get used because there never were any users. It was just the committee designing them. But fortunately, Haskell isn't like that. Haskell started off its life as an academic language. There are a lot of people, writing papers that, were honestly wouldn't have been possible without this language that let them say the things they wanted to do. And, in recent years, Haskell has had a lot of interest by people who, really want to use Haskell because it gives them more assurances. It lets them write things more concisely. And there's a decent industry showing for Haskell. So if you want to get a job writing Haskell full time, it's not completely out of the question. And so that's sort of where Haskell is right now. By the way, and we talked about this at the very beginning, but I just want to say this again. Homework 1 is out. It is due on Monday, so get started on it if you haven't already. Now we will switch to the second part of this class, which is live coding. And if people have thought up of questions, please shout them into chat while I'm getting ready. Okay, stop sharing. Yes. That's exactly right. So the question was, if Haskell is lazy, then when I write 1 + 1 in my program, does it really never get evaluated into 2 unless it is used? And the answer is yes. And in fact, now that I have my Haskell session open, we can do a little bit of an exploration on this. So, 1 + 1 is so fast, so you really won't be able to tell if it actually got evaluated or not. So let's just... Okay, I want to go into this, but let me just get started. And let me just make sure Twitch is seeing the correct screen. I think it is. Yes, it is. Okay, great. So, so before I dig into this example, I just want to talk about what kind of setup I have right now. So I have installed Haskell using the default operating system distribution. So if any of you are running Linux or have a Linux server handy, I just, this is Ubuntu, so I just apt installed GHC on it. On my Mac, I use GHC up to install it, and it actually got automatically added to the path for me, so I'm not sure why it wasn't working for the person who sent me on Windows. But hopefully, if you wanted to follow along, you've got a Haskell a compiler installed on your machine, or you're on a machine that has one. And what I've done right now is I've created a little file called basic. And this file is going to be the file that I'm going to put non-trivial code in. In Haskell, to define a module, you just say module and then the name of the module and then where. And then we'll put all the rest of our stuff. By the way, in Haskell, comments are done with double dashes. They're not done with slashes. So that's just how it is in Haskell. So you might be like, okay, I want to run my program. How do I run my program? And there is a way to run a program, but because we're not going to be talking about how to like do sequential, impure input-output things, there will be a much better way to run our programs to start with, which is we are going to use the REPL. The REPL, short for read eval print loop, is basically a way you can write little Haskell programs and run them and then see what their outputs are. So what I've done is on my terminal, I've opened up my module file with GHCI. So GHCI is short for GHC Interactive. And once I load up this file, it loads up the file. Well, the file is very boring. It doesn't have anything. But now I have this command line, which I can use like as a glorified calculator. So for example, if I ask it what 1 + 1 is, it tells me the answer is 2. I lost the chat window, so let me just bring the chat window back. Okay, so please holler questions whenever, because the point of doing this is live coding. Yeah, the file is module basic where. There's a question which is how do we exit GHCI? So you can either say :quit, or you can also do Control-D, and that'll also take you out. Okay, so let's get started with the lecture. Sorry, I'm pulling up my notes. Okay, so there's a few things going on, and what I want to start off with first is how we declare things in Haskell. So I've already seen that basic expressions that you'd expect to work inside the REPL, what we're going to be interested in is how we actually define these things inside of our program. So let's get started and let's see if we can do some bindings. So inside the module file, if you want to bind a variable, you say x equals and then something. So here's a number, and then if I reload GHCI using :r, short for reload, I can now access this variable that I defined inside of my module. So x has been defined to be 1, 2, 3, 1. Furthermore, when I define things in Haskell, I can give them a type. So what this says is that x has the type int, the machine size integer. The ::" just means has the type of. And then I say what the value of it is. And so if I reload this, I can ask GHCI what the type of a variable is using :t, and it says, hey, x is an integer. Checking for questions. So I mentioned that Haskell is a pure language, so x has this type forever. So if I try to reassign x to be some different value later, GHC will complain at me. It'll say, hey, there are multiple declarations of x. Which ones did you want? So we can only ever have one binding of x ever at a time. But I can, of course, make a new variable that still makes reference to x. And for example, what's x + 1? And now I have x and I also have y in this situation. Any questions so far? Okay, so that gives us a sort of glorified calculator where we can define values. And so I just want to tell you a little bit about some of the basic types available in Haskell. So we have integers, as you've seen so far. We have all sorts of basic operations, as you would expect. Do we have to declare the type, or will Haskell try to guess the type in question? Well, you saw that I could write this instead. And when I reload, everything is fine. and they do what I expect. Although when you when you ask what the type is, in fact, Haskell decides that x is not in fact an int, but it is an integer, which is the type for arbitrary precision integers in the language. Haskell has a built-in arbitrary precision type. It can be as big as you want. So like I can do something really, really big. But I haven't told you how to do that. So let's just go through some basic things. So you can do addition, subtraction, etc. If you want to do modulus or integer division, because as you saw, this gave us fractional division, there's a mod and a div function. So there's a few things that I need to explain very shortly, but the syntax for doing integer division is you do 2 and then backtick mod, backtick 3. And what is happening here is mod is an infix operator. That's what the backticks mean. And so if you try to do %, I don't even know what will happen. Okay, % is not actually defined to be modulus by default. So you've gotta use backtick mod. And div does the same deal. Sorry, div is integer division and mod is modulus. So we've got arbitrary precision integers. So this would get truncated if you try to run it, and then it gives you a nice warning saying the literal overflowed. But if you say it's arbitrary precision, then you get to save all the things. What other things does Haskell have? It has Booleans. So you've got true and you've got false. What's the type of true? Well, type true is just a Boolean. And you have your sort of usual logical operators that work on these things. By the way, to do negation, it's not an exclamation mark. Instead, you use the not. This looks like a keyword, but actually it's not a keyword. It's just a plain old function. There's a question, which is, are functions with symbol names infixed by default? And the answer is yes. So if you have a symbol, yeah. So something that's a little interesting that I was trying to get away with not telling you until later is that this ampersand and this not, they're actually just functions. They're not keywords. They're not special forms. They are good old-fashioned functions. And the rule in Haskell is that if your function is done with symbols, then it's infix. And if it is done with letters, then it is not infix, and you put it at the beginning. So now that we're here, there's some other types which, like you can do strings, and you can do floats. Well, you can do floats, Haskell. Yes, we'll see what this means a bit later when we do type classes. And yes, to finish off the question here, if you have a normal function, you can make it infix by doing ticks on it. So in fact, this is also a valid thing, and that computes the modulus 2 mod 3. That's what it computed here. This is good, and so it's a good time to explain how functions work. There's a question, by the way, which is, why did it say float twice? And the reason is because by default, the printer types out what the expression you wrote was. So the expression I wrote in this situation was 0.23 : float. So it tells me, oh, well, the type of that is float. And why did I? Oh, yes. So one more thing that I didn't say is, why did I write : float? Well, sometimes GHC will infer a type that is a little too general. Like, for example, when I gave you this integer, it told me it was a, well, more stuff that I don't want to tell you about right now. So when I defined an integer in my file here, I got an integer. So if I wanted to not do that, and I didn't want to write a top level binding for that, I could have just explicitly said, hey, the type of this should be that. And now I will find out that x is an int in this situation. Okay, so more questions? I love the questions. Keep them coming. So this is a good time to talk a little bit about how functions work in Haskell, right? Because if you can only define integers and strings at the top level of your program, that's pretty boring. There is one quick question, which is, what does infix mean? And that just means that when you write your expression, the operator goes in the middle of the two things. So 2 plus 3, it's in the middle, and that's why plus is an infix operator. If you've ever like looked at prefix notation, like in Lisps, sometimes you have to write the plus at the very beginning, and it's kind of awkward and not very intuitive. And so infix just lets you put it in the natural place. Okay, so let's talk about functions. So how do I write a function in Haskell? Well, we've already looked at how to call some basic functions, right? So we called mod, which I'm claiming is a function, and I passed it 2 arguments, 2 and 3, and it gives me the result of this. And I also told you that not secretly is a function. And so functions in Haskell are a little unusual. So in normal programming languages, you would call a function by saying f, f is a function, then call it with some arguments with parentheses and commas. But in Haskell, we write functions so often that we don't want to deal with writing out the parentheses and commas all the time. So in Haskell, when I want to do function application, I just do it by what I call juxtaposition, by like literally just putting a space. So if I have some function and I want to call it, I just say, okay, space, and then the argument, and then space, and then the argument. So this means that, for example, if I wanted to ask what the modulus of 2 plus 3 was, I have to actually properly parenthesize the inner expression, because the space doesn't bind very strongly. So if I wrote this instead, I'd get a very confusing error message, namely, yeah, I'm not going to tell you why you get this error message in this case, but this doesn't work, and you have to parenthesize the internal things if you've got internal messages, internally function calls. And that, by the way, applies to function calls as well. So like if I wanted to ask what mod div here was, well, I have to do that. There's a question, which is, does mod take plus since it's a first class function? And the answer is no. Although that's a really good question, which is, so like, for example, if I did this, well, the error message is a bit difficult to understand, but what has happened here is I attempted to pass div as a function to mod as its first argument. And mod is a very specialized, let me write some simpler functions for a moment. So, okay, I want to answer your question, but I need to do a brief detour. So let's write a little function. So in Haskell, I said Haskell is all about types. So when I want to write a function, I'm going to write out its type signature to start. And so this type signature is a little different than what you've seen before. It's int, arrow, int, arrow, int. And I'm going to tell you how to read this. So what you should do is you should look at all the arrows, and everything to the left of the rightmost arrow, those are the arguments separated by arrows. So this is a function that takes 2 arguments, an int and an int. And then at the very end, you get the return type of the function. You get an int at the end. So this is a function that takes 2 integers and then produces an integer. By the way, why is it done all with arrows? Well, I'll tell you why in next lecture, 2 lectures time. So to actually define this function, we're going to define an equation. So remember that I said that to call a function like mod, I just juxtapose the arguments with it, right? So it stands to reason that if I want to define what a function does, I'm just going to say, okay, well, if you call f with x and y, then I want you to do something with it. Like maybe I want you to add x and y together. So f is a just glorified version of add. So now I have a function. If I ask what its type is, it is int and an int. And then if I pass it some integers, I indeed get 5 in this situation. Yes, to keep it mathy, exactly. So I want to answer the question, which is, so what happened when I passed mod in? Well, this is very reasonable now. So if I said f mod 3, I'm not sure what I meant to do in this situation, but if I read the error message, it actually is very reasonable. So it says, couldn't match expected type int with actual type integer to integer to integer. And it even suggests probable cause mod is applied to too few arguments. And if I think about what's going on, well, f, I said, is a function that takes 2 integers as arguments, right? But mod is not an integer. Mod is a function. And in fact, it is a function that takes 2 integers and produces an integer. So Haskell very nicely says, well, I was expecting an int and you got an integer to an integer to an integer. So that's not going to fly. Now, if I said f plus 3, that would be different. This actually is, I try to add this function f to 3, and I get this thing, which is that, well, this doesn't work because there's no instance for num, which I have to wait until we do type classes to tell you about it. But if you actually wanted to pass plus as an actual function, there's a little trick. You just wrap it in parentheses. And now, once again, I'm passing in an integer to integer to integer function when I was expecting an int. This is not, I don't think you need this for the lab, but yeah, that's how you turn symbols back into regular fixity. So regular function, turn it infix by adding backticks. You've got a symbol, turn it into a regular function, or prefix, as you might think, by putting parentheses around it. How do we feel about using $$ for application? $$ is great, use it a lot. Let me just explain what $$ is and why you might find it useful. So let me think. So let's do some calculating. So let's say that I want to write a function like f3, and I want to, like, do some complicated thing at the end. It's not that complicated, right? 3 plus 2 plus 3. Some people really hate writing the parentheses on the last argument in this situation, and it's a lot more prominent when you're calling functions that only take a single argument, because like I want to do blah and then have a really big expression afterwards. So there's this special operator called $, which is actually just a function, and $, basically says everything to the right of it, take that as an expression and use that as the argument in this question. So if you don't know what this is about, don't worry. You can do everything you could do with $, using parentheses, but it's fine to use it in this situation. What precedence is normal function application? And the answer is function application, aka the space, has the lowest precedence for everything. So whenever you have a plus or a times or a power or anything like that, you must parenthesize it or it will not work. Will this work? This won't work. It'll tell me that there's some error. Yeah, you got the instance no num int. By the way, the reason why this error shows up is because Haskell is very general, and what it actually is trying to do in this situation is it's trying to use this. Actually, what is going on here? It's got a function, and it is trying to look up and see if there's an implementation of the caret, aka exponentiation operator, for a function, and that's what's going on here. Except that, why would you exponentiate functions? That doesn't make any sense. So you get this no instance error. We get a lot of complaints in the academic community about how Haskell is not that friendly for teaching, because I have to like gloss over stuff like this when I'm telling you about it in the very beginning. Okay, so I've told you how to define a function, and so we have passed the realm of being a glorified calculator. We use spaces to define where the arguments are, and when I want to define a function, I just define a bunch of arguments, and then I can write some expression that makes use of them. So that'll get you decently far, but I mean, we're still kind of a glorified calculator if we're only dealing with integers. So now I need to teach you about recursion. So let's do a simple program where it's the so-called hello world of functional programming. I want to define a function factorial. By the way, there's a question from Twitch, which is, what does module basic where do? And in our simple programs that we'll be looking at in this class, it doesn't really do anything. It's just some throat clearing you have to do to define a module. If I didn't have this, it wouldn't work. Would it work? It would work actually, but it would say my module was called main rather than say my module's name. So I'm naming my module basic just to make it an actual module. There's another question, which is, how do we denote code blocks if something spans multiple lines? That's a great question, and yes, the answer is we use indentation. So Haskell is an indentation-aware language like Python. Okay, so we're going to write factorial. What is factorial? Factorial is a function that basically sums up. So you should know what factorial is, but 5 factorial is 5 times 4 times 3 times 1. And so this seems a little difficult to write in Haskell given all the things we've looked at so far, because I've just told you how to define functions and how to define variables. So like, how are we going to actually define factorial in this situation? And the answer is, well, we're going to use recursion, right? So in a traditional programming language like JavaScript, for example, a very crappy way of writing factorial would be to say, well, if x equals 0, then return 1, else recurse by calling factorial on x minus 1 times x. And that gives you a recursive definition of factorial. So let's look and see how we would translate this code into Haskell. So in Haskell, there is an if then else syntax. So it's what you'd expect. So if don't mind me. So if x equals 0, then, and in Haskell, I said everything is expression based. So you don't need to return explicitly. If you just have some value expression, then that's what the entire expression is going to evaluate to. Else, and then we said we wanted to return factorial x minus 1 times x. So how are we going to do this? Well, we need to do a function call. And once we do this function call, I want to actually multiply it by x. And once again, no return needed. And this looks pretty familiar. And if we load it up and we take a look, hey, it actually gives us something reasonable. And you know, if I make this work on arbitrary precision integers, and then I give it some ludicrously large number, Haskell will happily go away and start computing it. By the way, oh no, is it stuck? It's not stuck. By the way, you can tell Haskell is lazy because if I, for example, assigned x to some variable, for whatever reason, you can't do this. Oh, you can. Oh, they fixed this. If I assigned factorial to a variable in GHCI, it's instantaneous. And why is that? Well, it's because Haskell is lazy. So it's only when I actually ask what the value of x is does it start thinking. Do I have a less ludicrously large example? It doesn't matter. It's too big anyway. Okay. So here's my factorial, and what we're going to see is that whenever we want to write like code that does what you would have done using a loop, we're going to do it with recursion instead in Haskell. And this implementation has some problems, but we will also talk about why this implementation has problems at a later point in time. But I want to introduce you to some language features that help us make this a bit nicer. So the first thing enhancement that I want to tell you about is pattern matching. So what is pattern matching? So pattern matching says that when I'm defining factorial, I don't always have to define the arguments as just plain old x or y or some variable that defines what the variable is going to be. I can say, well, when factorial is 0, I want it to be 1 in this situation. And this works, and I can run factorial on 0 in the situation, and I will get 1, right? It's a very equational style. It's like when factorial is 0, give me 1. And what's actually going on is I'm saying, hey, do a pattern match on the argument, and if it is a 0, then return 1 in the situation. And in fact, if I pass any other argument to it for this, it'll say, hey, you didn't tell me what all the other cases should be. So let's go fix that and just say if factorial is anything that's not a 0, and so now I'm doing a plain old function call, then I can do it like this, and that works just fine. There we go. Once again, shout questions in the chat if you have any questions. So there is still a problem with this factorial function, which is what if I pass in a negative number? I don't remember if I have to put parentheses around it. And the answer is it just loops infinitely. Because, well, I said that if it's 0, it's 1, but otherwise, subtract 1 from it. And because these are arbitrary precision integers, I'm not even going to overflow. I'll just, run out of I'll just keep going and going. So what I'd really like to do in this situation is I might want to say, well, if x is less than 0, then do factorial. Otherwise, don't. And so there's another feature in Haskell called guards, which let us do this in a concise way without having to write that if then else branch. So guards are basically a way of writing multiple equations for a function. And the way their syntax works is so instead of writing an equal sign directly, we're going to write a new line, and then we're going to put a pipe that just says this is one case. And then on the right side of the pipe, I'm going to write down the Boolean condition that I want to apply in this situation. So if x is less than or equal to 0, then 1. Otherwise, I want it to compute this factorial in this case. And now I will properly get a 1 in this situation. By the way, the spacing here doesn't matter. I could have deleted it. I just like lining up the equal sign. It makes my code look prettier. Okay. Any questions so far here? So we're still using Haskell as a glorified calculator, but it's a glorified calculator with recursion, and the recursion means that we can, write arbitrarily complicated software. Okay, so now I want to tell you about lists, because lists are a very important data structure in Haskell, and you'll be using them quite a bit inside the lab. So how do you define lists? Well, list literals work in much the same way that you might have expected in other languages. So you can define a list using square brackets. If I ask what the type of this is, it'll tell me, well, if I have a list of Booleans, what will it tell me the type is? It'll say, well, the literal list, which has true as its first element and false as its second element, has a type. And the way to read this is list of bool. So the square brackets are used in those cases. There's a question: are we going to discuss where and case of? I'm going to let's do case of real quick, and I'll tell you about where in a moment. So sometimes you can't conveniently do a pattern match. So let's revert this code back to the original version where I was just pattern matching. So sometimes you can't conveniently do the pattern match at the left-hand side because it's some intermediate result and you want a pattern match on the inside. And so there's another language construct you can use in this case called case. So what this says is do a pattern match on x. If x is 0, then I want my result to be 1. And if the result is, well, anything else, then I want the result to be this expression. So how do you write a case? Well, you say case of the thing you want to case on of. You have to increase the indentation when you get here, and then you write your pattern matches in the same way. But you don't use equal signs, you use right arrows afterwards. The indentation can trip people up. So some basic rules for when to indent is if you're writing, here's a multi-line equation, and in this particular case, when I want to keep defining this function, I have to indent in this case. And when I do a case, and in any case, most other language constructs that are kind of like this, I have to indent again. Otherwise, Haskell doesn't know, where the cases start. What happens if I do this? I got an error. Oh, okay. It has to be at least the same indentation or greater, and I tend to indent it further because it looks better. There's a question on Twitch, which is how come we didn't need spaces for x minus 1? And the answer is, well, it's an infix operator, so Haskell lets you omit the spaces because it knows that you can have an identifier that also has a symbol attached to it, so it's unambiguous in that case. And I will tell you about where in a little bit. Okay, so back to lists. So we've got lists. We have their type. Haskell lists are what we call homogeneous. So everything in a list has to have the same type. So I'm not allowed to have a list of strings and then also have a Boolean in it. It'll say, hey, well, you gave me this string. and by the way, strings are actually lists of characters. So like you've already seen lists. And this first element, which is a list of characters, aka a string, it doesn't match the second element of this list, which is just a Boolean in this case. If you want to have heterogeneous lists, you're going to have to do things. And when we talk about algebraic data types in a future lecture, we'll see how we could go deal with that. So obviously I can define an empty list. What's the type of an empty list? Well, interestingly enough, Haskell says, hey, the type of an empty list is a list of A. What's A? Well, A could be anything. We don't really know what it is. And Haskell's just saying, hey, I don't know what this type is. Well, you can figure it out later. Like if you want it to be a list of empty list of Booleans, sure, it can be an empty list of Booleans. You want it to be an empty list of ints? Sure, it can also be an empty list of ints. And this is our first encounter with what we say is polymorphism in Haskell, which we'll also look into in more detail in a later lecture. So, okay, so we got some stuff with lists, and let's look a little bit about how we can play around with lists. So for example, let's say that I want to write a function that computes the length of a list. So let's start off and, let's say I have a list of Booleans and I want to know how many elements are in it. So how would I go about doing this? Well, I could do this a very crappy way, which is I could like just start defining the cases one by one, but this clearly won't work if I need it to work for lists of any lengths. It certainly works okay when I have a list that isn't too long, but like it'll not work if I have a ton of things in the list. And once again, to do some sort of looping, which is what you normally would have done if you had a programming language that didn't, have a primitive for computing lengths of lists. By the way, Haskell does have that primitive. It's just the length function. But we're redefining it because we can, and it tells us a little bit about pattern matching. So if I want to do something like this, I need to, once again, rely on recursion. So, so this first thing that I wrote is pretty reasonable. It says when I call length on an empty list, I want it to be 0. That's my base case. It says what I should do once all the data is gone. But what should my recursive case be? And here I have to tell you a little bit about what we call the cons operator in Haskell. So this is a colon. It's an infix operator, just like plus and just like minus were. I put in spaces here to make it more clear. And what the colon does is it basically appends an element onto a list. So let's say I have a list 2, 3, 4. If I want to put a 1 at the beginning of the list, I can say 1 colon and then that list, and it gives me a new list 1, 2, 3, 4. And in fact, this is how lists are defined, and we'll get to this in more detail in the ADT lecture, but lists are either empty or some element consed onto the rest of the list. So because cons is like this, I can also pattern match on it. And this is like one of the really, really useful things about pattern matching in Haskell, right? Like if I have a data type that's non-trivial like a list, I can deconstruct it into its little bits. So just to like see a little bit what this is. So like let's say I have a list 1, 2, 3, 4, and I want to pattern match on it with x colon x's. So what do you think x is and what do you think x's is? Well, I said that when I do 1 colon 2, 3, 4, I get 1, 2, 3, 4. So x is going to be the first element of this list, and x is going to be the rest of the list. So, so what I'm going to do, well, in good old-fashioned recursive style, I want to call length on the tail of the list because x's is now smaller, so eventually I'll get down to 0. And whatever the length of the tail of the list, the length of x appended onto the beginning of the list with x's is simply 1 more than that. So now I have a function that will tell me the oh, sorry. This function only takes Booleans. And I find out that it's 3. If I wanted to make it take any element, and I'm getting ahead of myself, I could have just replaced the bool with, once again, a, and that just says, well, anything's okay. And now I can call len on 1, 2, 3. Once again, shout questions into the chat. Okay, so we talked about how to add elements onto the beginning of the list. How can you add elements onto the end of the list? And unfortunately, there's not a, you can't just say cons in this situation. And this is a terrible error message, but basically what's going on is that the right-hand side of cons has to be a list and the left-hand side has to be not a list. So if you want to add it on to the end of the list, there's a handy infix operator ++, which just concatenates two lists together. In fact, this doesn't have to be a single element. It can be multiple elements in this case. Okay, so let's, yes, question. That's correct. So what is going on is this is actually a concatenation operation, and it's creating an entirely new list that has 1, 2, 3, and 4, 5, 6, and it has to rebuild. It essentially conses 3, 2, and 1 onto 4, 5, 6. This wasn't true with the colon operator because remember I said Haskell is pure and immutable, and what it actually is these are singly linked lists, and we're just reusing this list in this situation. There's another question, which is how come I can't write this in my Haskell instance? And the reason is probably because your Haskell is too old. So you just have to tack on this let keyword at the beginning. Now's a good time to talk about let and where, I guess. So let's say we're writing a more complicated function. I haven't done any really complicated functions. But let's say that I had a function that needed a bunch of steps, and I wanted to define a bunch of intermediate. I wanted to define a bunch of intermediate values while I was working on them. So like Frozzel is going to first compute y to be 2 plus x, and then z to be 3 times y plus x, and then it'll return z times 4. So how do I write this? Well, there's two ways I can do it. So one is using the let keyword, which we just saw GCI used to force you to write in the REPL. And so you just say let. You can do as many bindings as you want. You just have to separate them with spaces. And then you have to say in. So how does this work? Well, basically it says define these bindings. And then the expression that I want to evaluate in the end is z times 4. And this will work, and I will, be able to Frozzel some numbers. There's another way that I can do this, which is called where. So what you can see is that this is kind of annoying, right? Because it sort of gets up in your way. And what if you just wanted to find a lot of things out of the way without having to upfront declare everything? So you can do that, and that's using this keyword called where. So this does exactly the same thing. It says Frozzeling x is equal to z times 4, where, and then once again you have a bunch of bindings separated by new lines, which tell you all the things you want in the situation. So once again, if I Frozzel 4, I still get 88. Is there question is there a difference between let and where other than syntax? And the answer is no, there is no difference. However, I can use let anywhere an expression would have been okay. So for example, I could let w be z plus 3 in w times w, and that would be fine. But if you tried to put a where in there, that wouldn't work. So wheres are only for when you're inside one of these functions, and then you just wanted to find a bunch of stuff for your function, so you tack on a where, and then you do some stuff. By the way, calling attention to indentation again, I have to indent, right? So this where clause is part of the function. It's not accessible anywhere else. If I ask for y, it'll say y is not in scope. So y is only in scope for this function, and so that's why it's indented. Thank you for all the questions. Okay. So, I need to do some more examples. So let's do another example, and we're going to do a very traditional example, namely reversing list. And this will be a good follow-up on the question that was, isn't append really inefficient? And the answer is yes. And we're going to do an inefficient version of reverse first that uses a bad version of append. So what is reverse going to do? Well, reverse is going to be modeled off of the standard library reverse, which takes the list and flips all its elements around. So how do we do this? So So once again, we're going to think recursively, right? We're going to be like, how do I tackle this problem and turn it into a bunch of simpler problems that I can solve and then assemble together to find the real solution. So once again, what's my base case? My base case is just what if I want to reverse an empty list? And reversing an empty list is, well, just the empty list. Easy. And then I'm going to pattern match. And now, what am I going to do? So if I know that I have a list and the head of the list is X and the rest of this is X's, well, first I want to recursively reverse X's. So let's use our newfangled where thing, right? So reversed X's is going to be calling rev0 on X's. And now what do I want to do? Well, I've got a reversed X's. I've got, in my example, I've got 3, 2, and I want to put 1 at the end. And as I said, I can't use the colon operator in this case. So I'm just going to use append to get this going. And indeed, this will work. And I can even test it on a very large list. What is this list syntax, by the way? It's just defining a sequence of numbers between 1 and, say, 100. So 1 to 100, inclusive both sides. So I can reverse this, and indeed it will reverse it in this situation. Now, someone pointed out that appending in this way is very inefficient, and in fact this function is quadratic, and we can see it if we give it a relatively large thing. It's kind of taking a while to print out all the things, and if I ran a regular reverse, it would actually be instantaneous. Well, not instantaneous to print, but instantaneous to figure out what the result is. So why is this function so slow? The reason this function is so slow is because, as I said, we are rebuilding all of reversed X's every time we go around. So here's a better way to do it. And this is going to use a little trick called an accumulator. So we're going to start again, and this time what we're going to do is we're going to write a helper function. So I don't know what I'm going to put here, but we're going to write a helper function. So instead of trying to do everything with expressions, what if we build up the result as we go along? And the sort of idea here is that when I have a list like 1, 2, 3, 4, I want to sort of build up the reversed list, and the build up of the reversed list is going to kind of look like, I'm going to start with 1, and then I'm going to put 2 in front of it, and then I'm going to put 3 in front of it, and I'm going to put 4 in front of it. There's a question on Twitch, which is, what is the underscore? And in fact, the underscore just means I don't know what to put here. And by the way, if it actually is valid syntax, and when I do that, it'll give me a nice error message saying, hey, there's a hole, there's a bunch of stuff, but basically I was expecting something that had type list of A in this situation. Pretty handy if you're working on your program and you're trying to figure things out. So, so as I said, what we're going to do is we're going to define a function that basically builds up the list as we go along, because, well, we start off with 1, then we cons 2 onto it. Sorry. Then we cons 3 onto it, then we cons 4 onto it, and lo and behold, we have a reverse list. So this is actually great and exactly what we want, if only we had some way of passing along the result in this case. So we'll have a result in this case. So, so the function we want to define is going to take the list that we're working on and the result, the reverse list, as we're building it along, and we'll return it in this situation. So what does this look like? So once again, we still need to think recursively. So we're going to be like, hey, when the list is empty, we'll just return what the result is in this case. And otherwise, when I have an actual list and I have the front and I have the back, what should I do in this case? Well, I'm going recursively, so when I go recursively, usually I want to make my function smaller in this case. So I want to go ahead and run this helper function on the rest of the x's. But what should I do with the result? Well, I said what I wanted to do was every time I'm building up this new list, I want to cons on the next element I see as I go. So what I'm just going to do is I'm going to cons on x in this situation. So I'm going to cons on x onto the results, and then I'll finally have my final result. And so how to actually run this? Well, let me just call my helper function with the initial list and then an empty result to start off with. And so this reverse indeed reverses, and it doesn't choke when I give it a really huge number. But you might not be convinced. You might be saying, hey Ed, I don't really know what's going on here. Can you go through it more slowly? And the answer is, yeah, I can go through it more slowly. In fact, I can have Haskell print out what the result, what result is every step of the way. And so here's how I'm going to do it. So I imported this module, debug.trace. So import in Haskell just brings all of the things that it defines in scope. And what I'm particularly interested in is in this function called trace. What is trace? Well, trace is a function that sort of is a bit naughty. What it does is it will print out whatever string you pass it when the thing is evaluated. I said Haskell is pure and trace is not pure. It's very, very not pure. So if you want to figure out if you've gotten somewhere, you just say trace, and then whatever string you want to print out, and then the expression that you were going to evaluate anyway, and that'll give you some debug printing in this situation. So let's once again run rev on a small example. And you see yo gets called 3 times because that's how many times we call this function. And you might be like, hey Ed, I want to know what the values of the variables were in this case. And so we can ask to show. Show is another function. Show will work on most types that we're working with in our basic Haskell classes. And we can just ask it to say, show what the accumulator looks like at this point in time. By the way, remember the parentheses bind very loosely. So I have to put these parentheses. If I don't put the parentheses, then, Haskell will be like, oh, this is a function with 3 arguments, show, rs, and then this go expression. So I need the parentheses in this case. Here we go. And what did I do wrong? Oh yes. So let's say we take lists of integers explicitly. Why this happened is a little tricky, but let's do this. And now when I call rev123, there's a bunch of things going on here. It might be a little clearer if I prefix the debug with a debug string. Remember, strings are just lists. So if I want to concatenate 2 strings together, I can still use the ++ concatenate operator. And what I'll see is that I have a bunch of debug calls. So first rs was an empty list, then it was 1, then it was 2, and then eventually I get this return value in this case. So this is pretty useful if you're not sure what's going on in your Haskell program and you want to find things out. But do be warned that these traces will come out in the order that Haskell actually evaluates them. So if you, for example, have a trace here, let's run a quick poll. Oh, I can't run a poll. Okay, I'm not going to run a poll. I'm going to tell you what's going to happen. So what happens if I run this hello here? Think to yourself, will hello get printed before the debug statements, or will it get printed after the debug statements? Give you a few seconds to think about it. I reload. Okay, let's run it. And hello got printed before we ran everything else. But now, what if I say move hello into here, So now it's on the empty list in question. When will the hello get printed in this case? And because I'm like presenting this as a question, you might guess there's something funny going on. Although, oh, that's interesting. That is not what I expected. Why did that happen? Did I save? I did save. Okay, I've tricked myself. So what I was going to say is that this wasn't going to get printed until we got to the end. Okay, I'll have to figure out why this example didn't work. I am doing this live. But there may be cases, and I guess this is a case in point, which is that the debug prints will not go in the order you expected them to, and that's because Haskell is executing things in the order you don't expect. There's a question from chat, which is, if trace is impure, how are we able to use it in a pure function? And the answer is, trace is, oh yes, Twitch gave me the answer, which is that it's because I'm showing RS here. So let me just run this real quick. And now hello's at the end. In fact, it's at a very strange spot in the output. And the answer is, well, we're cheating. So in particular, debug trace is cheating. It's got a very special implementation that lets it call into arbitrary input-output, even though you're in a pure context. And that function is called unsafe perform IO. It's terrible. You shouldn't use it, but it's there. And it's very handy for us in situations like this, where, as Twitch stream says, you know, tracing is like morally pure. It's not really doing anything. You're just trying to debug your code with it. And so it feels okay to do it this way. For you dollar fans out there, isn't it annoying to write those parentheses? Well, you could have put $1 there, and then you don't have to add parentheses when you're adding trace statements. Just something to think about. That's one of those situations where tracing is helpful. Oh man, we are out of time, and I have not told you everything you need to know for the lab. So I'm going to push the due date for the lab until Wednesday. I'll put an announce for this, and we'll get more on it on Monday lecture. Any more questions before we break? Yeah, so the question is, because Haskell is lazy, when it decides not to evaluate 1 plus 2, is it just, you know, holding on to the whole evaluation tree, 1 plus 2 in this situation? And the answer is yes, it is. And indeed, if you don't pay attention, you may have all of these so-called thunks, these things you haven't evaluated left, and they'll be taking up lots of memory, and it's actually a huge problem because you're running out of space. And in fact, this is one of the main reasons why people really don't like laziness, is because it's very hard to reason about space usage in this situation. So there's some tools for dealing with laziness, which I'm not going to teach you about in this class. Yeah, you do have to be careful about this when you're writing Haskell code. All right, so it is 6:10. Thanks everyone for joining, and see you all on Monday, and I will write that announce. Yes. That's a great question. So the question was, on the lab, how much do we care about performance and cleanliness? And the answer is, I need to communicate this to my grader, but I don't care about performance. So as long as you can get it to work, that's fine. For cleanliness, obviously, I'm not going to expect you to write like Haskell as if you've been writing it for the past decade. But, you know, try to like, you know, if you think something looks really awkward and like terrible, it's probably because it is. And, you know, like, see if you can figure out, you know, if there's one of the features, like maybe putting it in a helper function, doing a let block, something like that. That'll help you out. in those situations. All right, thanks everyone.